Okay, so today we have our final discussion on entropy. We're talking about the entropy balance. And if you notice here in the homework assignment, I crossed off one of the problems, 143. It's not a bad problem per se, but I think it's somewhat underspecified. So we're actually going to do that problem in class today because I think it's an interesting problem and an interesting example to use. But the way that they presented it in the book, you have to make a lot of assumptions, and they don't say that you should make those assumptions. So we'll do it together in class, and we'll kind of see how that works out. Moving on. Okay, so up until now, we've talked about entropy in the general sense. We've talked about what it is, what it means, how we find it. We've also talked about the principle of an isentropic process, meaning that it's a process that is adiabatic and reversible. And we use those isentropic processes to compare our real processes. It determines how close we are to achieving the maximum work output or the minimum work input. With the exception of the case of compressors, where the isentropic case is good, but we can do even better by actively removing heat from the compressor as we perform the compression process. So when we talk about an entropy balance, it's important to make some distinctions between entropy and energy. Okay, we know that energy also has to balance, and that energy cannot be created nor can it be destroyed. It can change forms, but it has to balance, and that accounting comes from the system and the surroundings. Okay, entropy also has to balance, but in this case, we can create entropy. So when we perform the entropy balance, we have the entropy in minus the entropy out plus this entropy generation is equal to the change in the entropy of the system. Okay, with energy, it was just simply energy in minus energy out equals change in energy. But for entropy, because we can create entropy through having irreversibilities in our process and through heat transfer, we have to account for this additional term. So entropy is a property value. We can look it up in the table. So if we have a set state for our system, and we know, say, temperature and pressure, or maybe temperature and specific volume, we can go to the tables and we can look up the entropy value at that state. Okay, so as we move from one state to another, our entropy will change. So we'll have not only the entropy change due to changing states, so at state 1 it's a certain value, and at state 2 it's a certain value. We will also have some entropy generation that is dependent on the process. Okay, so the amount of entropy you have at each given state is dependent on the state and the properties at that state. But the entropy that you generate depends upon the process. So if the process is a reversible process, your entropy generation would be 0. Okay, if there's no irreversibilities associated with that process, then you're not generating any entropy. The more irreversible it is, the more entropy that you will generate during that process. Okay. So if we have a steady state system and it's operating at steady flow conditions, then we can say that the change of the entropy of the system over time is 0. So this is actually ds dt. So if our fluid properties are not changing as our system operates, meaning that the inlet conditions are constant and the exit conditions are constant, then we won't have any change in entropy over time in our system. We will, however, have entropy coming in and out of the system. So we'll talk about that a little bit later. If we have uniform flow, then we can just assume that the properties of the inlet are some constant value. Again, we look that up in the table. If it's not uniform, then we find some average property value, and sometimes we have to average over the cross-section. We don't do that in this class. In further classes, we would. So the entropy can be transferred into the system by 2 ways. The first is by heat. So we've talked about how heat transfer is an irreversible process. It adds entropy to the system when you add heat to the system, or removes entropy from the system as you remove heat. And then we can also now transfer it in by mass transfer. So similar to the idea that energy is transferred into a system due to the energy state of the mass as it comes in, so that there's some energy associated with the flow, there's also entropy associated with that flow. So there's entropy coming in at the inlet and entropy leaving at the outlet. For steady flow problems, there's no accumulation of entropy within the system, meaning over time it's not increasing within that system. Similar to how we would look at energy transfer due to mass coming in and out of the system. If it were an unsteady flow system, which we don't do that for entropy in this class, then we would have some entropy change over time. So as heat is transferred in and out of the system, we have to determine how we are going to recognize that heat transfer at the boundary. Okay, so heat is disorganized energy, and by nature has a lot of entropy associated with it, the higher the temperature of the heat source. So for an isothermal boundary, if we're transferring heat at a constant temperature, then our amount of heat, amount of entropy transfer due to heat is just simply Q divided by T. So the amount of heat divided by the temperature at which it crosses that boundary. If the temperature is not constant, then we would have to find some average associated with the amount of heat transfer at each different temperature through the system. Again, we don't do this in this class, any of the problems that we have, but it's important to know that this is a generalized form of the equation, is Q over T. Okay, additionally, the mass coming in and out of the system has entropy associated with it, and it's proportional to the amount of mass that comes in. It'll also be proportional to the rate that the mass comes in. So if we have mass coming in at a certain rate, then the increased rate will increase the flow of entropy into the system, just as it would for energy. And as a mass enters the system, it brings entropy with it. As a mass leaves, it removes entropy from the system. So adding mass to a system will increase the entropy. Removing mass in general will decrease the entropy. The exception would be as if you're adding mass of a lower entropy value, and so you're decreasing the overall entropy of the system because you're pushing out some of the mass with a higher entropy value. We'll see how that all balances out in the end. And then again, if the properties aren't constant at the inlet and the outlet, then you have to average them and find some net entropy value as the properties change over the cross section. Energy can be added to a system or transferred to a system by work, but entropy cannot. Okay, there are irreversibilities associated with work that can contribute to the entropy generation within the system, but work itself does not transfer entropy into a system. So if we have boundary work on a piston cylinder device, for example, we add energy to our system as we compress that boundary. We don't add entropy to the system by compressing the boundary. We only add entropy by mass and by heat. Okay, so it's important to note that distinction between the transfer of energy and the transfer of entropy. And again, this points out the differences between the first law and the second law, because by the first law standards, heat and work are equivalent. But by second law standards, heat and work are different forms of energy, they have different uses, and they perform a different role in the energy and entropy balance within the system. Okay, so now let's talk about entropy generation. And we've mentioned before that irreversibilities in the system will cause more entropy to be generated. So a list of some of those: friction, mixing, chemical reactions, heat transfer, unrestrained expansion, non-quasi equilibrium compression or expansion. Okay, these are all things that we can imagine will cause our system to be less efficient. So they will add entropy to the system, or entropy will be generated due to the irreversibilities. And again, this entropy generation term is a measure of how irreversible that system is. So the greater the entropy generation, the greater the irreversibilities within the system. And as we're performing our entropy balance, we're just looking at the system itself, not the system plus the surroundings. We can create a new system to include the surroundings, but as we do our entropy balance, we're just looking at the entropy change of the system and what's coming into that system, out of that system, and generated by that system. Okay, we don't look at the surroundings. We sometimes need to use the temperature of the surroundings to determine the boundary temperature of the system, but for determining our entropy balance, anything that's happening outside our system is usually irrelevant. We would just need to know heat transfer and temperature, or any mass flow that comes from somewhere else. And then again, If our system is internally reversible, meaning that we can change direction, reverse the process, and it will look like it never happened, then our entropy generation is 0. Okay, so there are real systems that can be approximated as internally reversible and have 0 entropy generation. They're not perfectly internally reversible, but they can be close. Totally reversible systems, where they leave no effect on the surroundings as well, they are much, much more difficult to approach and don't usually exist in real life. Okay, so some different forms of the entropy balance. This is just in per unit mass. This is just in the normal mass form, and then of course the rate form. And where we talked about for a steady flow system, this ds dt is equal to 0. And if it's a reversible process, then all of these entropy generation terms go away. We don't generate entropy during a reversible process, so it just simplifies down to S in minus S out is equal to the change in the entropy of the system. And this is similar to energy balance. There's no energy generation in a process, so these look very similar to the energy balance equations that we've used before. So let's talk more specifically about how it applies to the different types of systems that we've studied. In this case, we're going to look at closed systems and open system. So if entropy is transferred by mass flow and by heat transfer, in a closed system, which of those two will you have? Or we have both or none? Looking at the board. Okay. So you will only have entropy transfer due to heat. There will be no entropy transfer due to mass flow. And why not? Because it's closed. There is no mass flow in a closed system. So if we look at our entropy generation equation, we are going to find all of the entropy in and out of the system due to heat transfer, and then the temperature at which that heat transfer occurs. So this is like S in minus S out. It's only due to the heat transfer, plus the entropy generation is equal to the change in the entropy of the system. If the system is an adiabatic system, meaning there's no entropy or there's no heat transfer in and out of the system, then the entropy generation is just equal to the change in entropy of the system. So if there's work done on the system, the irreversibilities within that system can lead to a change in entropy state. So there can still be an entropy change in the system even if there's no heat transfer in or out, as it changes state or goes from one entropy level to another. Okay, because again, entropy is a property value, and we look it up at the initial and final states. And then if we want to include the surroundings within our system, we call this an isolated system. Then the entropy generation is the change in entropy of the system plus the change in entropy of the surroundings. So we can just expand and include that. Okay, any questions on closed system entropy balance? Okay, we're going to do an example. So imagine a person. We can approximate a person as closed systems when they're just standing there holding their breath. Okay, so for heat transfer purposes, we'll just assume that they're a 30 centimeter diameter, 170 centimeter long vertical cylinder with both the top and bottom surfaces insulated and with the side surface at an average temperature of 34 Celsius. Okay, so a very generalized person. If the rate of heat loss from this man to the environment at 20 Celsius is 336 watts, determine the rate of entropy transfer accompanying heat transfer in watts per Kelvin. Okay, so we know Q dot out is 336 watts. We know the temperature of the boundary is 34 Celsius, the boundary of the man. The temperature of the surroundings is 20 Celsius, and the dimensions of this person. So how do we determine how much the rate of entropy transfer to the surroundings? I guess the first question would be, how is entropy being transferred out of this system? Heat loss. Okay, so Q out of this system, or Q dot out is 336 watts. So S dot out is going to be Q dot out divided by the temperature of the boundary of our system. So in this case, we say the boundary temperature is the temperature of this person, 34 Celsius. So it's 336 watts divided by 307 Kelvin. So that's 34 plus 273 Kelvin is equal to 1.09 watts per Kelvin. Okay, so that's just the amount of entropy transferred out of our system due to the heat transfer from this person and the temperature at which that heat transfer is occurring. Okay, let's do another example. This time we have heat being transferred through a system. So we have a brick wall. On one side of the wall is 20 Celsius. On the other side is 5 Celsius. And then the surrounding temperatures on the outside of the wall are 27 and 0 Celsius respectively. Okay, so it's hot outside, cold inside. And then there's some heat being transferred through this wall. It's 5 meter by 7 meter wall with a thickness of 30 centimeters. So the question is, if the rate of heat transfer through the wall is 1035 watts, what is the rate of entropy generation in the wall and the rate of total entropy generation associated with that process? Okay, so what is our system in this case, or what do we want to choose to be the system? Okay, the wall is our system. So we have one boundary that's at 20 Celsius and another boundary that's at 5 Celsius. Okay, so let's write the energy balance for our wall. The temperatures of the wall are not changing with time, so we can assume that there's no that it's a steady heat transfer through the wall, but it's not changing with time. Okay, so S dot in minus S dot out plus S dot gen is equal to ds of the system dt. Okay, our wall's not continuing to get hotter, so we know that the net entropy change of the system over time is 0. Okay, if we knew something about how the temperature of the wall changed with time as this heat is flowing through it, then we would have some change in entropy with time. But we're assuming it's flowing steadily through, it's not changing with time. Okay, so do we have heat transfer into the wall, or do we have entropy transfer into the wall, I guess I should say. Okay, we have entropy transfer in due to the heat transfer in, entropy transfer out due to the heat transfer out, because this heat fluxes through the wall. And then we have some entropy generation within the wall associated with heat being transferred through it. Okay, so we can say that the entropy generation within the wall is equal to S dot out minus S dot in. Okay, so what is S dot out? Or what's another way of writing heat entropy transfer due to heat transfer? Okay, it's Q dot out over T. So the question is, which T do we use? Do we use 0 or do we use 5? Okay, why do we use 5? Okay, so the system is our wall, the boundary is at 5 degrees Celsius. Okay, so this is Q dot out over T of the boundary on the outward, or the outgoing side, which is actually the inside, I believe. I don't remember which is inside and out. Q dot in over the temperature of the boundary at the location of heat transfer on as the heat is coming in. Okay, so Q dot out is 1035 watts divided by the boundary of the wall, which is 5 degrees Celsius. We convert that to Kelvin, so it's 278 Kelvin minus 1035 watts divided by the temperature of the boundary on the other side, which is 293 Kelvin. So we determine the entropy generation in this wall is 0.191 watts per Kelvin. so this is the entropy generation within the wall. If we want to determine the total entropy generation due to this process, we now expand our boundary a little bit to include the system and the surroundings. So the temperature of our boundary is going to change, so that the temperature of the boundary on the hot side is going to be 27 Celsius, and on the cold side is going to be 0 Celsius. Okay, so this is just the entropy generation in the wall. If we do the wall plus the surroundings, our equation is the same. S dot gen is equal to S dot out minus S dot in is equal to Q out over T minus Q in, those have dots over them, over T as it comes in. Our Q dot is the same, it's 1035 watts. But in this case, the temperature of the heat, of the boundary where the heat is leaving as we've expanded our system is 0 Celsius or 273 Kelvin. And on the inside, the temperature that it's coming in is 27 Celsius, which is 300 Kelvin, and the heat flux is still the same. So 1035 watts over 273 Kelvin minus 1035 watts over 300 Kelvin, and we get 0.341 watts per Kelvin. Okay, so the entropy generation within the wall is 0.191 watts per Kelvin, and then the entropy generation due to this entire process, where we're considering the entropy generation in the wall plus the entropy generation in the surroundings, is 0.341 watts per Kelvin. So this is the system plus the surroundings.
So has anybody made any predictions like where the entropy generation rate declined?
I have not yet.
I mean, they're either just like put it in order of magnitude or anything.
I don't know. There probably are people who have done that. They've estimated, at what point the heat. But then I was reading something the other day that was talking about because the universe is constantly expanding, it's cooling. So I don't know if the entropy generation is greater than the cooling due to the expansion of the universe. So hopefully I'm not around to find out. Okay, any questions on this and the distinctions between the two calculations? So one, we're just looking at the entropy generation in the wall, and then two, we're looking at the entropy generation in the wall plus the surroundings. Okay, so closed systems are fairly straightforward. All we have to worry about is the heat transfer in and out and then the change of state. But for an open system, we now have mass flow in and out, and so we have to consider the entropy coming in and out of the system due to those mass flows. So the general form of the equation is here and then also in rate form. So the sum of all the heat transfer coming in plus the mass coming in and plus multiplied by the entropy of that mass minus the mass leaving multiplied by the entropy of the mass leaving plus whatever entropy is generated during the process is equal to the change in entropy of that control volume. Similarly, in the rate form, and as we've talked previously, this ds dt, or the rate form of the change in entropy of the control volume over time, will be 0 if it's a steady flow problem. So if there's no change in property values over time within the system, then the same would apply for entropy, that the entropy is not changing over time in the system. And then if it's a steady flow single stream problem, this simplifies down even further, where we have just one single mass flow rate and then the difference between the entropy at the inlet and the exit. And if it's steady flow single stream and adiabatic, we don't need to be concerned about heat transfer. All we need to worry about is the mass flow and the entropy associated with each of those fluid streams as they come in and out of the system, and then the rate of entropy generation. So to determine the rate of entropy generation for a steady flow problem, it's fairly simple and straightforward. We just move it to the other side of the equation and then solve for the effects due to the mass flow and the heat transfer in and out of the system. Okay, simple in terms of the algebra involved. But sometimes the problem comes when we are analyzing our system and setting up our system boundaries in the first place to determine what temperature the mass is coming in and out, and whether or not we need to worry about heat transfer. So you have, similar to energy balance, you need to define your system very well before you even start and make sure you understand what's happening at the boundaries of that system before you begin the entropy balance. Okay, let's do an example. So in this case, we have a throttling valve. We have steam at 7 megapascals and 450 Celsius, which is throttled to a pressure of 3 megapascals during a steady flow process. So we need to determine the entropy generated during the process, and then just check and verify if the increase of entropy principle is satisfied. And what is the increase of entropy principle? What does that say? So what has to be greater than 0? The change in entropy or the entropy generated? Entropy generated. Hey, our system can decrease in entropy. The system state can decrease, but our entropy generation has to be 0 or a positive value. Okay, so to make that distinction, to satisfy the increase in entropy principle, we may have a decrease in entropy in our system. If we're removing heat, the entropy will decrease. But the entropy generated has to be positive, or for the reversible case, it would be 0. Okay, so what do we remember about throttling valves that is special and important?
They don't involve work.
They don't involve work. There's something else about them.
They're highly efficient.
No. Depending on how you divide efficiency, but they don't require any work to bring about a pressure drop. They have a constant property value. What property is constant?
Temperature.
No. Not pressure, not temperature, not velocity, not specific volume. Enthalpy. Okay, so they're a constant enthalpy process. So if you look at the graph, then you would see that too. Okay, so we have steam at 450 Celsius and 7 megapascals. So we'll go to our tables, and we'll call that state 1, 7 megapascals and 450 Celsius. And we look up our enthalpy at state 1 is 3288.3 kilojoules per kilogram. And our entropy is 6.6353 kilojoules per kilogram Kelvin. Okay, the fact that this is a constant enthalpy problem allows us to fix the second state. So we're given a pressure of 3 megapascals at state 2. But we know also that H2 is equal to H1. So the enthalpy is constant. Otherwise, we would have no way to fix the second state to look up property values. It's not a constant entropy process for a throttling valve. They're not isentropic. They're isenthalpic. So H2 is 3288.3 kilojoules per kilogram. And S2 is 7.00455 kilojoules per kilogram Kelvin. Okay, so do we have any heat transfer during this process? How do we know that?
We're assuming it's
Okay, we're assuming it's adiabatic, but how can we make that assumption?
There's no little cube in the air on the
There's no Q. It didn't tell us in the problem, but there's another way to look at it. If we were to perform the energy balance on this system, if it's an isenthalpic device, meaning that enthalpy is constant, that would mean that there was no heat transfer and no work. Okay, if H1 equals H2, then it would have to be the case that there's no heat transfer and no work. Okay, so in reality, throttling valves will have a minuscule amount of heat transfer associated with them just because they're everything does. It's very hard to insulate things perfectly. But because it's isenthalpic and we're making that assumption, we by nature are assuming that it's also adiabatic. Okay. So if it's adiabatic, do we have any entropy transfer in this process? Okay, so is there any entropy change? Why?
It's not reversible,
Okay, it's not reversible.
so there has to be something generated.
Okay, there's entropy generated. And entropy is a property value. So if our initial and final properties are different, then we will have an entropy change. Okay, so let's look at our equation. So S dot in minus S dot out plus S dot gen is equal to the change in entropy of our system over time. Okay, it's a steady flow throttling valve. So we know that this side of the equation is equal to 0. So S dot gen is equal to S dot out minus S dot in, which is equal to M dot times S out minus S in, where these are now lowercase entropy values. We're not given the mass flow rate in this problem, so we can divide through by the mass flow rate, and we get a lowercase S gen is just equal to S out minus S in. Okay, and what is our entropy out? Okay, our entropy is leaving, or our mass is leaving the system with an entropy equal to S2, so 7.00455 kilojoules per kilogram Kelvin, minus the entropy coming into the system, 6.6353 kilojoules per kilogram Kelvin. So the entropy generated during this process is 0.36925 kilojoules per kilogram Kelvin. Okay, so this is on a unit mass basis. For every unit mass that comes into the system and leaves the system, this is how much entropy is generated during that process, just by it flowing through the system and changing the property values. Okay, are there any questions on this example? As you step through these problems, you apply the same types of analysis that you did for energy balance. But in this case, we're using just a different equation. Okay, so if you know how to look up property values, you know how to identify when there's heat transfer at a boundary, then you should be able to perform the entropy balance. Okay, let's do another one. This is the homework problem that I removed, and it makes a whole lot more sense when you actually have this little picture up here. But in this case, in the book, they don't have a picture. They just give you the problem statement. A family of 4 with each person taking a 5-minute shower every morning with an average flow rate through the shower head at 12 liters per minute. If city water at 15 Celsius is heated to 55 Celsius in an electric water heater and tempered to 42 Celsius before being routed to the shower head, determine the amount of entropy generated by this family every year as a result of taking showers. Okay, so with the picture, it's a little bit easier to know what they want. Because when I first started doing the problem, I started the problem with 55 Celsius and 15 Celsius coming into the system and having 42 Celsius leaving. What they actually wanted was the entropy generation due to the whole process, including that of the water heater. Okay, so you can do it both ways, or you can do it, it's 2 different ways, but one takes into account the amount of entropy generated due to the water heater, and one just takes into account the amount of entropy generated just by taking a shower with hot water, and not including the entropy generated by a water heater. Okay, so we're going to look at both because I think it's kind of interesting to see how much entropy is generated by a water heater. As we mentioned previously, that it's probably the most, has the greatest power consumption of any other electronic in your house or device, appliance, that's what I want to say.
So you're saying we could just draw a box and say, you got 15 coming in and 42 going out.
Right.
That's it, right?
Well, but you have 15 coming in on 2 lines. So there's city water coming into the house, and at one point it splits off and goes to the water heater, heats up, and then goes to the shower. On a different line, it's just coming straight in and then matching up with that hot water later again, and then coming out at 42 Celsius. Okay, so depending on where we define our system, we can do 2 different problems here. Well, we can do many different problems here if we just
Could
do
you
boundaries,
just assume
whatever.
that the main line comes in, and I understand how water heater works in brains, right? But before that, it comes in as one line.
Right,
So
yes. I mean, effectively, that's what you're doing when you have 2 lines. They'll have 2 different flow rates, but if you add them together,
that's what
yeah, and we'll see that come out in the problem. Okay, so let's just do the first case from the start. So it's coming in from the street, and we have these 2 lines. On here, I labeled these so this was 1, 2, 3, and 4.
Does the shower time of 5 minutes, that include the entire time that the water is running for each person?
Yes.
that includes you getting in, taking time.
This is out of the shower. You like charge.
You can't shave your legs, and you can use shampoo but not conditioner, and then you're done. For girls.
So we're talking about 60 liters of water a year.
That's a lot of water. Showers are very energy intensive. So think about that when you're in the shower and it's like relaxing and nice. And you're like, oh, I'm using up so much electricity and generating so much entropy
But
right now.
that's the best part of your life right there is in the shower.
That's the best part of your life. I'm so sorry for your life. No, I agree with you to a certain extent.
All the great knowledge that you pick up on in the shower is you can't put a price on this price.
It's true.
That's why to sit there and say that you're using up energy which costs money is just silly.
I don't know, color puts.
Sometimes you have to just enjoy it. Yeah, sometimes you just have to enjoy the energy you're using. So pick and choose how you want to spend that energy allotment. I would use it on the shower. Okay. So let's look at this problem. And if we want to determine the mass flow rates of each of those sections, we're only given the mass flow rate, actually we're given the volumetric flow rate out of the shower head. So let's convert that to a mass flow rate. So V dot 4 is equal to 12 liters per minute. And we're going to convert that into meters cubed per minute. So multiply by 1 meter cubed divided by 1,000 liters is equal to 0.012 meters cubed per minute. So m dot 4 is going to be equal to this volumetric flow rate divided by the specific volume. Okay, we don't know that yet. We can just assume it's 1,000 kilograms per, that would be density. 1 over 1,000 kilograms per meter cubed. Or we can go to our property tables and look everything up because we're going to need these values of entropy and enthalpy anyway. So I'll do that over here. We'll just go to the property tables, and you can either look up the fluid property values at these temperatures, so 15, 55, and 42 Celsius, or you can use ease to spit those out for you. I actually did this problem in ease because it was faster. So at 15 Celsius, we have our specific volume, V1, is equal to 0.001001 meters cubed per kilogram. F1 is 0.2242 kilojoules per kilogram Kelvin, and H1 is 63.01 kilojoules per kilogram. So this is state 1 and state 2, because they're both at 15 Celsius. So if we just look at where we define them. So then at 42 degrees Celsius, which is state 4, we have our specific volume is 0.001009 meters cubed per kilogram. Our entropy is 0.5989 kilojoules per kilogram Kelvin. And then our enthalpy is 176 kilojoules per kilogram. Then at 55 degrees Celsius, our specific volume is 0.001015 meters cubed per kilogram, so it doesn't change much the temperature. S3 is 0.7679 kilojoules per kilogram Kelvin, and H3 is 230.3 kilojoules per kilogram. Okay, so we've defined the properties at all these different temperatures so that we can use them in our equation. I think it's also worth it to just calculate the time involved is 4 people times 5 minutes per day times 365 days per year gives us 7,300 minutes per year. Is how much time that family spends in the shower. Okay. So now we can calculate our mass flow rate is V dot over the specific volume, which ends up being 11.89 kilograms per minute. Okay, I can do kilograms per second and then find my time in seconds, but I'm saving myself 2 steps. Okay, so let's look at case 1, where we're analyzing the entropy generation from the street. So S dot in minus S dot out plus S dot gen is equal to ds dt, which if this is steady flow, we're going to assume that they turn on the shower and it's steady immediately, and then they turn it off and it stops. Idealized. Okay, so S dot in is equal to m dot 1 S1 plus m dot 2 S2. S out is equal to m dot 4 S4 plus S dot gen equal to 0. So S dot gen, we can move it to the other side of the equation and solve for this. Okay, so if we do a mass balance on this, we know that m dot 1 plus m dot 2 is equal to m dot 4. We also know that S1 is equal to S2 because they're at the same temperature, the city water coming in. Okay, so we have m dot 1 plus m dot 2 times S1 minus m dot 4 S4 is equal to negative S dot gen. Okay, so we can solve for S dot gen, plugging in all these numbers. M1 plus M2 ends up being m dot 4. So it ends up being m dot 4 times S4 minus S1, which equals 4.46 kilojoules per minute. We plug in all the numbers for that. So M4 and then S4 and S1 from over there. Okay, so this is how much energy or entropy, kilojoules per Kelvin times minute. Okay, so this is how much entropy is being generated per time. Then if we multiply it by the time interval, so we multiply by the 7,300 minutes per year, so times 7,300 minutes per year is equal to 32,558 kilowatts per Kelvin times a year. Oh, wait. Yeah. Kilojoules, not kilowatts. Okay, so 32,558 kilojoules per Kelvin times a year. So that's how much entropy every year, each year. That's how much entropy is generated by this family of four in a year. Yes.
So, like a couple lectures ago, we learned this equation of like S2 minus S1 equals CP average times natural log.
You can also do it that way.
And like eliminate all of that.
Well, yeah. Yes. Okay, so now let's look at it from beyond the water heater. So how much entropy is generated just by taking a shower? Okay, so if we look at that, we have to go through now the energy balance to determine the mass flow rate. So we say Q dot in minus Q dot out plus work dot in minus work dot out equal to the sum of the mass flow rate out, m dot H minus the sum over the inlets of m dot H. We assume that it's adiabatic, there's no work involved, so the mass flow rate times the enthalpy out is equal to mass flow rate times the enthalpy in. So m dot 1 H1. Now we're starting past the water heater, so we have m dot 3 H3, so 0.3 is at 55 Celsius, is equal to m dot 4 H4. And we also know that m dot 1 plus m dot 3 is equal to m dot 4. So we can plug that into there, rearrange, we find m dot 3 is equal to m dot 4 times H4 minus H1 divided by H3 minus H1. So that equals 8.03 kilograms per minute. And then we can solve for m dot 1, which would be 3.86 kilograms per minute. Okay, so if we want to find the flow rates of the other two sections, then we can go back to this equation. So Sn minus S out plus S gen equals our change in entropy. So in this case, we have m dot 1 S1 plus m dot 3 S3 minus m dot 4 S4 plus S dot gen is equal to 0. So we solve for S dot gen is equal to m dot 4 S4 minus m dot 1 S1 minus m dot 3 S3. So if we plug in all the numbers for that, we solve for the mass flow rates, we have the entropies from the table. We find that S dot gen is equal to 0.089272 kilojoules per Kelvin per minute. So then we multiply again by the 7,300 minutes in every year. We find it's 651.7 kilojoules per Kelvin each year. Compare that to 32,558 kilojoules per Kelvin times a year. And we find that the water heater itself contributes 31,906.3 kilojoules per Kelvin times a year. Okay, so of the shower taking process, the vast majority of it is just due to heating up that water. If you want to take cold showers, then your entropy generation will be much less. But you'll be a much unhappier person. Okay, any questions on this problem? Okay, the alternate way of solving it is you just assume it's constant specific heat and you use C sub P and then the equations for entropy of a liquid from a previous section, you can solve it that way too. And the answers are very close. I like using the table, but that's just me. Okay, so let's do another example. This time we do use C sub P in this heat exchanger. So we have a shell and tube heat exchanger used to heat hot water, to heat water. So this would be like your water heater, where C sub P is 4.18 kilojoules per kilogram times Kelvin. And it heats it from 20 to 70 Celsius at a rate of 4.5 kilograms per second. Heat is supplied by hot oil, C sub P equals 2.3, that enters the shell side at 170 Celsius at a rate of 10 kilograms per second. So disregarding any heat loss from the heat exchanger, determine the exit temperature of the oil and then the rate of entropy generation in the heat exchanger. Okay, so this problem is similar in that it's a steady flow problem that involves more than one fluid stream. But for a heat exchanger, the fluid streams don't mix, so we don't have to worry about multiple fluids coming in and out, so it's a single stream problem. Okay, so what information do we need to know in this problem? Or what sorts of things would be useful to us? If we need to find the exit temperature of the oil, so we know the inlet temperature of the water and the exit temperature of the water, and we know the inlet temperature of the oil. How do we find the exit temperature of the oil?
On the Q in of the water.
Okay, so we could find Q in of the water and then compare that to the Q out of the oil and perform the energy balance in that way.
And that's assuming that we have no extraneous heat loss.
Right. So everything that is lost from the oil goes into the water. Okay, so let's do that. So if we do the energy balance on the water, Q dot in minus Q dot out plus work dot in minus work dot out is equal to the mass flow rate of the water times H2 minus H1. So the outlet of the water is 2. So 2 and 1, like that. And then the oil, I did them separately, so I call this 2 and 1. Okay, so mass flow rate of the water times H2 minus H1, H2 of the water minus H1 of the water. Do we have any heat transfer into the water?
Yes.
Yes, the oil is hotter than the water. We don't have any heat transfer out, and there's no work involved in this process. So Q dot in is equal to the mass flow rate of the water times H2 minus H1, or because we're given C sub P of the water, we can say it's C sub P times T2 minus T1. So this is 4.5 kilograms per second multiplied by 4.18 kilojoules per kilogram Kelvin multiplied by the temperature difference. And again, when we have a temperature difference, we don't have to convert to Kelvin first. We can just find the difference in the Celsius, so 70 minus 20 Celsius, so 50 Celsius total. So that equals 940.5 kilojoules per second for Q dot. Okay, now we can perform the energy balance on the oil. And in this case, we don't have a Q in, but we do have a Q out. So it will end up being negative Q out is equal to the mass flow rate of the oil times H2 of the oil minus H1 of the oil. Or Q dot out is equal to the mass flow rate of the oil times the C sub P of the oil times T1 minus T2. So I flip the signs because of the negative here with Q out. So solving for T2 is equal to negative Q in of the water. Why did I do that? Okay, because then, so this is Q out divided by M dot C sub P of the oil plus T1 of the oil. So Q out of the oil is equal to Q in of the water. We just plug this in for Q out, and we get 129 Celsius. Okay, so far all we've done is the same energy balance analysis that we have done for steady flow systems in the past, finding the final temperature. Okay, now we need to do an entropy balance on the heat exchanger. Now that we know that temperature, it's part A of the problem. So if we do an entropy balance on the entire heat exchanger as our system, we have sum of Q dot K over EK plus the sum of the MISI minus sum of the M dot ESE plus the entropy generated is equal to DS dt. Okay, so we have the entropy change flux due to heat transfer plus the entropy change due to mass flowing into the system minus mass flowing out of the system plus the entropy generation of the process is equal to ds dt. So let's see what terms we can cancel out. If we're looking at the entire heat exchanger as our system, do we have any heat transfer? Okay, we have heat transfer within, but there's no heat transfer occurring at the boundary, so that term goes to 0. Okay, do we have mass flow in? Okay, we have mass flow in from 2 different places. We have mass flow out from 2 different places. We have entropy generation, and is our entropy changing over time? Okay, no, because it's steady flow. So let's just start writing out these terms. We have the mass flow of the oil times the entropy in of the oil plus the mass flow of the water times the entropy in of the water minus the mass flow of the oil times the entropy out of the oil minus the mass flow of the oil times the entropy, water, sorry. Oil, water, times the entropy out of the water. Plus S dot gen is equal to 0. Okay, so we can combine terms. We have the entropy generation is equal to the mass flow of the oil times S2 oil minus S1 of the oil plus the mass flow of the water times S2 water minus S1 water. Okay, so now because this is a liquid and we make the approximate assumption, which includes constant C sub P and incompressible flow, then we can say it's the mass flow rate of the oil times C sub P natural log of T2 oil over T1 oil plus the mass flow rate of the water, C sub P of the water times the natural log of T2 water over T1 water. Okay, so that's one of the reasons why we had to solve for T2 of the oil to put it in these equations. Now in this case, it is important that these are in Kelvin because there's not a temperature difference, it's a temperature ratio. It has to be converted to Kelvin. So the mass flow of the oil is 10 kilograms per second. C sub P is 2.3 kilojoules per kilogram Kelvin. Natural log of 129 plus 273 Kelvin divided by 170 plus 273 Kelvin. But the mass flow of the water is 4.5 kilograms per second. C sub P of the water is 4.18 kilojoules per kilogram Kelvin. Going under the board, sorry, natural log of 70 plus 273 divided by 20 plus 273 Kelvin. Okay, so we plug in the numbers for that. This part we determined to be a negative 2.23 kilowatts per Kelvin. So that's the contribution due to the heat transfer from the oil. It's a negative, and then this part is 2.96 kilowatts per Kelvin. Okay, so if we add those two together, we can see that the entropy is being reduced due to the heat transfer out of the oil, being increased by a greater amount due to the heat transfer into the water. So this S dot gen, 0.730 kilowatts per Kelvin. That's the total entropy generation of the heat exchanger. Okay, so we can do each part individually and calculate them, and we can do them together to find the total entropy generation of the heat exchanger. Okay, any questions on that example? Okay, get started on your homework. I do have one additional homework hint on problem